Okay, so welcome back, everybody. This is your sixth tutorial for Comp 335, in which we'll be continuing our discussion of the pumping lemma and closure properties by looking at a few more exercises. And then I'm going to review grammars with you, just review some exercises of deriving strings given a grammar, and then I'm going to briefly introduce context-free grammars because it's also another way for practicing derivations, and I think that will be a useful tool for you to have before the midterm. All right, so let's get right into it. Pumping lemma and closure properties. So the first exercise here asks us, and actually all of the exercises here are going to ask us if the language L, which in this case is the set of strings that look like a to the n, such that n is not a perfect cube. So is this language regular? Okay, so that's our question, and we need to prove our claim. If we state that it is regular, we need to either create an FA that accepts it, create a regular expression that denotes it, or create a grammar that generates it. Otherwise, if we think that it's non-regular, we need to prove it using the combination of the pumping lemma and the closure properties. Okay, so well, what are we thinking for this one? Well, essentially the intuition that I want to give you here is the fact that n is not a perfect cube is going to be very difficult for an FA to keep track of. Okay, so it's not something easy when we're saying that n is mod 2 equals 0. So that's super easy to keep track of in a FA. But for n is not a perfect cube, it's a bit trickier because we'd want to accept something like a to the, let's say, 4, because that's not a perfect cube. But we won't want to accept a to the 8 because this is 2 cube, right? So this cannot be expressed as k to the cube, but this can, and so we won't want this in our language. And essentially, it's going to be very difficult for a simple machine, a simple FA that has no memory whatsoever, to keep track of such strings. Okay, so that should be kind of the intuition behind the answer, is that for more complicated languages, you're going to need to have some memory. So we're going to see that at some point you're going to use a stack, and then at some point you're going to use even more sophisticated types of memory that a typical computer would use. And so in this case, having an FA that knows nothing of what happened in your string before it's going to be impossible actually for any of us to create an FA that kind of keeps track of these strings. Okay, so what I'm going to claim that L is not regular. Okay, so now I need to prove that. So the first thing you could do is you could just do pumping lemma alone. But that's going to be very difficult here because you're going to have to find a formulation for your string W. So remember, what you have to do in the pumping lemma is you have an integer greater or equal to 0, which is in the pumping lemma, right? So you have some integer m, and you want to create a string W that has length greater or equal to m, such that you're going to be able to essentially pump it up, pump it down after decomposition, and show that it's not in your original language. But this is going to be very tricky to do here, because it's actually going to be very tricky to correctly define an integer, sort of a string that is not a perfect cube. Okay, And so you can do it, it's possible to do it, but it's going to be a lot easier if we use the closure properties first. And another hint why we would want to use the closure properties is you have a negation here. So the not a perfect cube is a hint that you might want to use some form of closure property. So what I'm going to do here is I'm going to first assume for the sake of contradiction, right? Because I mean, even when you're doing a pumping lemma, the first step is you're assuming that L is in fact regular for contradiction. The same thing is going to happen here. If you don't assume something, then it's going to be very difficult to start the proof. So that's why non-regular proofs, we usually start by assuming, for the sake of contradiction, that in this case L is regular. Okay, so what does that mean? Well, if L is regular, then I know that L complement, this guy is also regular by the closure properties, right? Okay, so how does that help us? Well, I know that L complement is now going to have all of these strings a to the k such that k is a perfect cube, union some other stuff. So I know it's going to have other strings, okay? But I don't really care about those strings. What I care about is, in fact, these strings here in this language. And this should be sort of coming back to you that we kind of did an exercise like this in the previous tutorial, where we actually showed that a language like this was not regular. So that's going to be a hint, okay? Because right now L complement is essentially the union of these kind of two languages. So what we want to do now is we want to apply another operation to L complement so that I can isolate essentially only this guy. Okay, and that's what I'm going to do. So I'm going to take L complement and now I'm going to intersect it because I only want the strings that look like a to the something, right? So to do that, I'm just going to say I want L of a star. So this tells me, this guarantees me that I'm going to have a to the something. And the fact that I'm taking L complement guarantees me that I'm either going to have a to the k is a perfect cube or something else. But because of the intersection here, because of the property of intersection, what I'm going to get as my resulting language L prime is going to be the set or the language a to the n, such that n is a perfect cube. Okay, so I'm essentially what I'm doing is I'm using the intersection property so that all of my strings are going to look like both this and this. And the only way for that to happen is for my string to be a sequence of A's, so a sequence of A's, and also a perfect cube. So those are the elements, the strings that are in common. Okay, and so I know that this guy is regular, right? Because I've just written a regular expression that denotes it. And I know that the regular languages are closed under the intersection operator. So this would mean that this guy here, the sort of conclusion is that L prime is regular. But now remember from tutorial 5, we actually showed using the pumping lemma that L prime was actually not regular, right? So what does this mean? Well, this means that we have arrived at a contradiction. Okay, and that was our goal, essentially. Our goal was to find a way to reach a contradiction. And the fact that we have a contradiction means that our initial assumption, in this case, that L is regular, was false. And so if the assumption that L is regular is false, then this must mean, so this implies that L is not regular. Okay, and this would be a complete proof. Of course, you would have to add in the details for the pumping lemma, but for the pumping lemma to show that this isn't regular, but I invite you to consult tutorial 5 for that. And so using this process, we've arrived at the conclusion that L is not regular. And maybe a more general question then is, if L is not regular, can L complement be regular? So this is a general question that we would have sort of from this instance, this problem, this instance of a problem. And in fact, this can never happen. So you can never have L complement regular and L not regular. Why? Well, if L complement, if this guy is regular, we know that regular languages are closed under the complement. So if I complement this guy, this is also going to be regular. But L complement complement, you're essentially taking the complement twice. It's like kind of when you do minus minus. So this would give you the set or the language L itself, and L is regular just because you kind of follow the same, you essentially apply the regularity of L complement complement to just L because they're the same language. And so I have that L is regular. So in fact, this is never possible. Okay, so if this was a multiple choice question, then you could immediately kind of think of this property, and even without having to do kind of this whole process, you could directly say, you could kind of check this off as not regular. Okay, so hopefully that's clear. If it's not, you can always shoot us an email, and we'll be happy to sort of re-explain or explain further. All right, so the next question here is another, is it regular or not? I have the following language L, where L is the set of strings A to the N, B to the L, such that N over L belongs to the integers. So this is actually from your worksheet. I think it's the worksheet on closure properties and pumping lemma. And so if some of you already attempted this question, then this might be a good opportunity for you to check your work. Although the solution I'm going to give is not necessarily the only solution, but let's see one way of doing this. So I feel like everyone is going to have the intuition that this is not going to be regular. So L is not regular is going to be my claim. And the reason why I say this is it's kind of similar to the example before. Tracking N over L being an integer actually requires some form of memory, okay? You kind of need a buffer to distinguish between an integer and not an integer. So it's very difficult to picture an FA that would be able to tell you, oh yes, this is an integer, or oh no, this is not an integer, because you're trying to do a division, right? And there's no division operator in an FA or in a regular expression or in a grammar. So the fact that this operation is so complicated means that an FA is essentially too simple to accept this form of language, this type of language, and that's going to lead me to believe that it's not regular, okay? But now I need to, of course, prove that. So what's going to be the proof here? Well, here it's going to be difficult, I admit, to use closure properties. You're not going to have a choice but to directly use the pumping lemma. Okay, but here you're going to have to, I'm going to show you're going to have to be very careful when you pick your W. Okay, so how does the pumping lemma go? Well, let's assume for the purpose of contradiction, so this is what that stands for. I'm just using it to go a bit quicker. Well, not to go quicker, just because it takes long to write. So assume for the purpose of deriving a contradiction that L is regular. Okay, so L is regular, and because L is also infinite, right? I mean, the number of strings in here never ends, right? You can keep creating strings because the set of integers is also infinite, right? So because L is also infinite, we can apply the pumping lemma. Okay, so remember the condition to applying the pumping lemma is that you're given a language L that's infinite and regular. Okay, so I have my conditions for the pumping lemma. Now I can apply it. So let's say, say M is the integer in the pumping lemma. Okay, so I have my integer M. Now what I need to do, so this is probably step 1. Now what I need to do is I need to pick a string W in L such that the length of W is at least M. Okay. So here, this is, I always get the question, you know, how do you know how to pick W? And really this is a matter of practice. And it's kind of a matter of thinking ahead to see how you could pump up or pump down. Okay. So the idea here is I'm going to have a string that looks like A to the something, B to the something, right? And preferably, I'm going to want to have at least M symbols here, right? So then what I'm going to do is I'm going to be able to decompose X, Y, Z here. So I'm going to know that my Y is going to be only A's. Okay, so I'm just giving you the intuition here. So my Y is going to be A to the K, or K at least 1. And then what the process is going to be is I'm going to want to pump up or pump down. And so what I'm going to want to know, I'm going to want to show rather, is the thing that was on A, so the exponent, let's say for A, let's say plus IK if I'm pumping up, over the exponent for B is what I want to show is that this is not in the set of integers. So of course, I'm not restricting myself to plus. It can also be minus, and you're going to see that I'm actually going to pick minus. Okay, so this kind of problem reduces to how can you easily show that a number is not in my set of integers. Okay, so I agree that at the beginning isn't so obvious, but because I have a fraction here, the hint is actually that I have a fraction. And I know that if I have something like P over Q, where P is less than Q, well, I know that this implies that this, sorry, let me just write this. The fact that the numerator is less than the denominator implies that this is not in Z. So that I know for sure. So that's kind of a hint. Or that's kind of where you should be heading in your kind of reasoning, is that it could also be, it would be maybe just a bit more difficult given the situation that you show that B was strictly larger than Q, because then, you know, you could have a multiple of Q and then it would be a bit tricky. So that's why I'm going to use B is strictly less than Q. P, sorry, is strictly less than Q. If that's true, and I know for sure that P over Q is not an integer. Okay, so that's where I want to head, essentially. So how can I do this? Well, let me clean this up a bit. So I'm just going to want to keep this. So I'm going to kind of want to show this. So the way I can do this is I can start, remember initially what I want is I want this divided by this to be in Z, right? I want my string W to be in L. And for that to occur, I need the first exponent to be divisible by the second exponent. I'm going to make my life very easy here. What I'm going to do is I'm going to pick m plus 1. And you're going to see in a second why I picked plus 1. And I'm going to pick b as m plus 1. So clearly, I hope everyone sees that if you take m plus 1 and you divide that by m plus 1, you get 1, which is clearly in the set of integers, right? So w is in L. And furthermore, the length of w is 2 times m plus 1, which is strictly greater than m, so I'm good for that. I know that the length of w has to be at least m, and I have that. Okay, so I've picked my string w. Now, I'm going to show at the end why I picked m plus 1 instead of m. But suppose for now that I have a to the m plus 1, b to the m plus 1. Now the third step is I'm going to want to either pump up or down. And the hint from here is kind of telling me that I'm going to actually want to pump down. So the only way to pump down is that I'm going to want to pick, well, just a reminder, to pump down, I just mean that I have w to the I. I'm going to want to have w to the I, which is equal to x, y, I, z. So remember, I can decompose w as x, y, z. And my y here, because I know that xy is less than or equal to m, my xy's are going to be all within my a's, right? And because my xy are all within my a's, my y is actually going to be a string of a's. So I'm going to just write a to the k for k greater or equal to 1, right? So I know that by the kind of second assumption for the pumping lemma. And so I know that the result of these two things is that if I pump up or down, I should have a string that belongs to L. But here I'm going to show that this doesn't happen, and that's going to lead to my contradiction. So as I was saying, I'm going to want to pump down here. So what I'm going to do is I'm going to want to set I to 0 here. So well, what does this look like? W to the 0 is just going to look like x, y, 0, z. So that's just x, z. So then just imagine this as being, you're taking the m plus 1 a's. So you have your m plus 1 a's. And then you know that you have k a's in y. So you're just going to remove, k a's from your m plus 1 a's. So you're going to get a to the m plus 1 minus k. Okay. And then your b's are going to remain unchanged. So you're going to have a to the m plus 1 minus k, b to the m plus 1. And now, because I want to derive a contradiction, I want to show that this is not in L. And this is true because m plus 1 minus k is strictly less than m plus 1. And that's because k is strictly greater than 0, sorry. So if you have, let's say if you have a number x, which is less than a number y, then x over y is never in the set of integers. And so this is true. It's true that the pumped down string is not an L, but the pumping lemma tells me that for any pumping number, so for any I should always have my resulting pumped string to be an L. And so what I have here actually is I have a contradiction. So I have a contradiction, which implies that my initial assumption was incorrect, i.e. that the assumption that L is regular was incorrect. And so in fact, L is not regular. Okay, so one last thing. Why did I say that I wanted to pick a to the m plus 1, b to the m plus 1. So why didn't I choose, like I'm sure some of you must have started with, a to the m, b to the m? Well, the reason for that is very, very subtle. Okay, so suppose that you did choose to pump down again. So suppose you chose a to the m. So then you had the result here would have been a to the m minus k, and then b to the m. All right. So the issue here is that this should work for any m and for any k. So that's what the reason for picking m and k as arbitrary is because you wanted this to work for any m and for any k. But now, if there's an opponent, I'm essentially trying to win a game against my opponent where my opponent is allowed to say, okay, well, you're claiming that m is arbitrary, but is this going to work if m is equal to 1 or if m is equal to 2 and so on, okay? So I'm not allowed, remember, I just want to make this clear, I'm not allowed to say m is equal to 2, right? This is forbidden for me in the proof, but the kind of, the game I'm playing is I'm playing against this opponent where that opponent is going to try any of the possible m's, and he's going to want to see if any of those break, for my argument. And it's actually true that this is my argument. If I were to pick m here and m minus k here, it's possible that saying a to the m minus k, b to the m is not in L because m minus k over m is not in Z. This is not always true, okay? And the reason for that is because I know that m can be greater or equal to 0, and I know that k can be greater or equal to 1. So let's say my opponent is very lazy and he says, okay, I'm going to test this person's proof with m equals 0 and k, sorry, not m equals 0. He's going to use m equals 1 and k equals 1. Okay, so he's going to test my proof, meaning that he's going to say, okay, this person assumed that A1, B1 is in L. And then he said, A1 minus 1, B1 is not in L. Remember, the opponent is the one that's picking the ones here. You can never, I really want to, I can't emphasize this enough. You can never pick a 1 here. You always have to keep m arbitrary and k arbitrary. But if you want to think of a reason why your proof does not work, then you can play the role of your opponent and say, okay, well, if I pick m as 1 here, and then I pick k as 1 here, then does my proof hold? In other words, does this statement that a to the 1 minus 1, b to the 1 is not an L, is that true? Well, unfortunately, we all know that a to the 1 minus 1 is going to be a to the 0, and I'm going to have a to 0, b to the 1, right? And so I'm claiming that this is not an L, but this is not true. And the reason for that is because I'm going to be taking 0. Remember the definition of L? Definition of L is the exponent for A over the exponent for B should be in Z. And the contradiction, if I want to always have a contradiction, then that should never be true. I should never have that my exponent here when it's divided by this exponent here. That should not be in Z. But for this case, if I take 0 and I divide that by 1, I get 0, and this is in Z. And so my opponent who's very clever, was able to find a particular setting here where my proof doesn't work. And so that's the reason why I had to pick m plus 1 here, because m plus 1 guarantees that the top here is at least going to be 1. And because I'm doing m plus 1 minus k over m plus 1, I know that this guy, which is going to be at least 1, is going to be smaller than this guy, which is going to be also at least 1, but that doesn't really matter. And I know that that's never going to be in Z. Okay, so I know this was very long. I know I'm actually going a lot over the time, but I really wanted to explain that correctly, because making sure that you pick the correct setting for W is one of the most difficult parts of the pumping lemma and of actually the first half of the course in general. Okay, so what I want you to take away from this is the first thing: you can never set in your proof particular values for M or for K, but if you want to check if your proof does work, then maybe you can say, oh, well, if M is something and K is something, is my argument also going to hold? But of course, you can't do this exhaustively, because M is greater or equal to 0, so it can be arbitrarily large, okay? But this, I hope, was clear, and I hope the kind of subtlety there was kind of understood. Otherwise, as always, you can just email us. Okay, so moving on. We have another question here, which is another, is L regular? So in this case, I don't have a restriction on the form of L. I just have that W is in the alphabet, or sorry, W is any string over the alphabet AB, such that the number of A's plus the number of B's is equal to 4 times the number of B's. So this might seem very scary at first, but what you can do, and you're allowed to do this, is you can just take this equation, subtract NA on both, or sorry, not NA, subtract NB on both sides, and now you'll just get that NA is equal to 3 times NB. So in other words, that the number of A's should be 3 times, thrice the number of B's, okay? And again, very similar to the intuition from before, my claim here is going to be that L is not regular. And again, this is because your machine should somehow keep account of your B's, and then verify that taking 3 times, thrice the number of B's should give you your A's. So that's not something that an FA or a regular expression or a grammar can handle, a regular grammar at least can handle. So that's why I'm going to claim that L is not regular. And here you could use closure properties to maybe make the pumping lemma proof simpler, but really it's not really going to be a big issue here, because there's no restriction on the form of W, so I can really pick any W I want. So that's what I'm going to do. I'm going to straight away use the pumping lemma. So again, I'm going to assume for the purposes of deriving a contradiction that L is regular, right? So I'm assuming that L is regular. And so I know because L is infinite, the pumping lemma applies. Okay, so again, what's step 1 of the pumping lemma? You want to pick an integer m, and let m be the integer which is greater or equal to 0 in the pumping lemma. So that's just saying, remember that integer in the pumping lemma? Well, that's going to be m in this case. Okay, so that's your first step. The second step is going to be pick a W and L such that the length of W is at least m. Here, the W is going to be pretty should come to you pretty immediately. I mean, there's going to be lots of different ways of doing this, but the one that's going to be the easiest is going to be W A to the 3M B to the M. Okay. So you could pick this one. You could also pick something like B to the M, A to the 3M. Right? You could there's different ways of doing it, right? But let's just say that I'm going to pick this guy. Okay. So now 3, actually I kind of skipped a step in 3. I should have formally decomposed the string W for you. So I'm going to decompose W as X, Y, Z. So I know that W is a bunch of A's, 3M times, and then it's a bunch of B's, M times. So let's say my X is here, my Y is here, and my Z is here. So I know that Y is going to look like A to the K for some K greater or equal to 1, right? And of course, this is because X, Y is less than or equal to M. So my XY is within the first M symbol, so it must be within the first MAs, right? So that's why my Y is just a sequence of A's. It's just a sequence of KAs. All right, so now what is the fourth and last step? Well, now I need to either pump up or pump down. Here, I'm going to say I'm going to, so I'm going to write it formally, pick an I such that Wi, X, Yi, Z is not an L. So here I'm just going to pick I is equal to 2, so I'm going to pump up by 1. So W2 is going to be X, Y2Z, or X, Y, Y, Z. So the only thing I'm doing is to the existing A to the 3M, I'm going to just add an extra Y, but I know that Y is just KAs, so I'm just going to add KAs here. And I'm going to finish that off with B to the M. And now I'm going to show that this is not an L. So for this not to be an L, I need to have that the number of A's is not equal 3 times the number of B's. Well, if you take the number of A's in W2, so this is W2, if you take the number of A's in W2, I know that this is 3M plus K, right? And because K is strictly greater than 1, I know that this is strictly greater than 3M, right? And I know that 3M is 3 times the number of B's. And so I have that the number of A's in W2 is strictly greater than 3 times the number of B's in W2. And so, of course, that means that the number of A's in W2 is not equal to the number, is not equal to 3 times the number of B's in W2. And so this implies that W2 is not an L. And that implies that I have a contradiction, right? Because for the pumping lemma, I know that the pumping lemma tells me that any pumped up string, pumped up or down, should be an L. So this is a contradiction. And so what this means is that my initial assumption was wrong, i.e. L is not regular. All right. So that's one way of showing it. Again, in the solutions here, I have B to the M, A to the 3M. You know, it doesn't really matter as long as it works for an arbitrary M, right? So in this case, if my opponent started to check all of the possible M's, he would essentially never be able to break my proof. And that's why it's a correct proof. All right, so the last exercise in proving that a language L is not regular or regular is going to be the following. So I'm going to want to know if the language L, where L is a union of A to the 2n, so in other words, the sequence or the string that contains a sequence of even number of a's, union a to the 2n, so the sequence of, so the strings that contain a power of 2 a's, right? I want to know if this is either regular or non-regular, okay? So you might immediately think, oh, a to the 2n, I saw this in the lecture, it's not going to be regular. And well, you'd be right, you'd be most certainly right that this is not regular. But if you have L non-regular and you do a union with L regular, this can either be non-regular or regular. So it's never always regular and it's never always non-regular. You have to be careful, okay? And in this case, you need to be particularly careful because it's in fact going to be regular. So my claim is that L is regular. Why is that? Well, what I'm gonna do is I'm gonna decompose L into L1. It's going to be this guy, and L2 is going to be this guy. What is L1? Well, I know what L1 is. It's just all of the strings of even length which has only A's, right? So lambda, A2, A4, A6, and so on. And what is L2? Well, L2 is all of the strings that has only A's and that has a power of 2 A's. So in other words, A to the 2 to the 0, A to the 2 to the 1, A to the 2 to the 2, and so on. So what is this? That's going to be A, well, 2 to the 0 is 1, so I have A to the 2 to the 1, that's A to the 2, and 2 squares is 4, so I have A4, and maybe I'll write another one, I have A8, and so on, okay? So what I actually want you to notice here is, other than A, all of the following, all of the next strings that I'm going to see are going to have an even number of A's. And why is this true? Well, because for k greater than 0, 2 to the k is even, right? And so maybe let me quickly show you why that's true, because if k is strictly greater than 0, then I can say that 2 to the k is equal to 2 times 2 to the k minus 1, and this is going to be greater or equal to 0, so this is just any integer k, let's say n, and so I have that the left-hand side is equal to the n, so it's even, right? So I know that all of the strings after a have an even length and are only a's. And so really what this guy is a subset of L1, right? And I know that if I take the subset of a set and I union it with that set, I just get the larger set, right? Because if I have A and A is a subset of B, then A union B is just going to be B, right? So the same thing kind of applies here, except that I have this pesky A. So what I'm just going to do then is I'm just going to write L is that pesky A, union, and then the union of, let me use a different color, the union of this guy with this guy, right? And what is that going to be? Well, clearly that's just going to be the larger set. It's going to be the larger set B, or in this case, the larger set L1, which is going to be lambda, A2, A4, and so on, okay? And so why is this regular? Why am I saying that this is regular? Well, that's because I can create an FA that accepts it, or a regular expression that denotes it, or a grammar that generates it. In particular, I'm going to create a regular expression because it's going to be sort of the simplest and the cleanest. if I write R, the regular expression, as A plus AA star, well, this guy is going to give me all of the strings of even length that only has an A, and this singleton here is going to give me that single A here. So I know that L of R is equal to L, and because R is a regular expression, that implies that L is regular. Okay, so here the main idea was just to be careful. Even if you have a non-regular language, unioning that with a regular language may give you a regular language, and sometimes they may not give you a regular language. All right, so that concludes the section. Oh no, it doesn't. So that concludes the part of the tutorial about showing that L is not regular. Here we have another exercise where it's actually about knowing what correct W to pick. So let me read out the question. I have the following language, A to the N, B to the K, C to the N plus K, D to the P. For NKP greater or equal to 0. Of course, we're assuming these are integers. And I have, this should be the integer M from the pumping lemma. And I want to know which of the following strings for W would be a suitable choice to show that L is not regular. So essentially, which W here can I pick that's going to work? Well, let's go through each choice. The first one here, I have A to the M, B to the M, C to the M. So all of my conditions for, let's say, W greater or equal to M, that's correct. Is W in L? Well, no, unfortunately, because here I'm supposed to have the number of C's should be the number of A's plus the number of B's. So I should have M plus M is equal to the number of C's, but in this case, this is not true because the number of C's is equal to M. So actually, A is not going to work. Is B going to work? Well, actually, for the same reason, B is not going to work because I have M plus M. That's 2M, and that's definitely not equal to the number of C's, which is 0. Okay, so this is not going to work. What about W? What about C, sorry? Well, so my length is greater or equal to M. Is W in L? Yes, well, because the number of A's is M, the number of B's is K, but in this case it's 0, and that's going to equal the number of C's, which is M. So W is in L, and let's see, if I were to pump up, yeah, so I could just easily say I pump up, I get W2, and I get A to the M plus K. So here I'm skipping a lot of steps just because it's a multiple choice question. So I will get A to the M plus K, CM, and then I know that this is not going to be an L because M plus K plus 0 is not equal to M. So maybe the K wasn't the best choice. I don't mean the K from B. I mean, let's say, because my decomposition x, y, z, where x, y is less than or equal to m, let's say y is going to be a to the s, so m plus s, right? And that's not going to be an L, right? So this is going to work. What about D? Well, so I have a dm here. It doesn't really matter what the D is. It can be 0. So here I have D to 0. But again, for the same reasons as before, the number of A's, which is M, plus the number of B's, which is 2M, is 3M. And this is not equal to the number of C's, which is N. So no, this is not going to work. All right. So now, right, that does conclude our section on the pumping lemma. So the next part of the tutorial is going to be about reviewing grammars. It's just going to be a few quick exercises about what's the string derived by the grammar. Okay, so these should take a little less time. So sorry I rambled on a bit before. I just wanted to make sure that everything is clear. Okay, so I have the following grammar here, G, and I want to know which of the following strings are going to be generated by G. The first thing that you can check for questions like this is G regular? Because if G is regular, then it actually makes your searching a bit easier, okay? Just because of the properties of regular languages, and sometimes you can find some tricks that are going to help you. Well, here I see that all of my production rules are right linear. So G is right linear, which implies that G is regular, right? So yes. Yeah, for this exercise, it might not help that much, but it will, you'll see it will for the next one. Okay, so which one of these is going to be generatable? Sorry, that's not a word. Which one of these can G generate? Let's look at the first one, AAAB. So I know I have to start in S, right? Because S is my start variable. To get an A, I can either go to S again, or I can go to A again. And I know that the only way I can terminate my string is with this lambda, right? And the lambda is connected to the B, and the B is connected to the A. So what I feel like is the easiest route here to check is I'm going to repeat an A and S a few times. So I'm going to give myself S gives me AS, and then AS gives me AAS. And now I'm going to want to switch to A because I want to get to that B in time to get the lambda. So I'm going to switch to A reading AA. So we're going to have 3 little a's and 1 big A. And then I'm going to skip this production rule and go straight to B. So I'm going to get AAAB, and then I can replace B. Then I can replace B with lambda, but that doesn't work, does it? No, so actually what I should have done is I shouldn't have skipped this first production rule. I should have actually gone through it. So in other words, this wouldn't have worked. What I should have done is I should have done AAA, and then replace that with BA, and then replace that with, so AQBB, and then I could have replaced that that variable B with a lambda, which gives me AQB, right? So here we see that that's derivable from my grammar G. Okay, the next one, BAB. Well, B for a string here to start with B, because it's right linear, I for sure have to go from S to BA, right? That's the only thing that when I start at S, I can get an A. Then, well, I don't want to use this guy because then I would get another B. So what I need to do forcibly, I actually need to go to B, capital B. Okay, and now what do I want? I want an A. So the only way to get an A is to do this one here, to do AB. So I'm going to replace B with AB. And now what options do I have? I don't want to stop here because that would give me BA. I don't want another A. I do want another B, but then if I want another B, I go back to S, and then there's no way of getting S gives me lambda. That's not going to be possible. So in fact, it's not going to be possible to derive BAB because of that process. All right. And in fact, maybe I'll skip C for now. Just look at D for a few seconds here. D, it's actually going to be the same reasoning. I'm going to use the same derivation sequence. I'm going to get to BAB, but now I'm going to replace B by another AB, right? And then I'm going to get stuck with the same problem. To get a b here, I need to replace my variable with bs, but then this cannot give me lambda. So that means that I'm going to be stuck. And so this guy is never going to be able to this string cannot be generated by G. And the last one, C here, BBA. Well, if I start an S, again, if I want a B, I want to replace that with BA. If I want another B, then I'm going to replace that with another, I'm going to be here, I'm going to replace that with another BA, excuse me. And then I'm going to replace, because I want to get to this A. Ooh, so it looks like it is possible. I'm gonna go to B, so I'm gonna go to B. And then I'm going to replace this B with AB. I'm going to replace this B with AB, and then I know I can replace that with a lambda, so I get BBA. So yes, I can derive this guy. All right, good. Okay, so that's how you would answer this type of question. There's another one here that I'm going to go a bit faster with. You're going to actually see a quick trick here. So again, I have the same type of question. I have the grammar G. Again, this is a right linear grammar. And what I want you to notice actually is because this is a right linear grammar and the only terminal rule is BB. Remember, what does a right linear grammar mean? It means that I'm going to have symbols, terminals here, and then I'm always going to have a variable here. So because it's right linear, I'm always, the last derivation rule is always going to be, you're going to replace the rightmost variable, which is the only variable, with x in x as a string of terminals. And so in this case, BB is the only string of terminals. So I know that my string must end with BB. So then I can already rule this one out, and this one out. So this is kind of a trick for you in a multiple choice question if you're time constrained. So now the only thing left to do is to check, well, is C can C be generated by G? Well, I have to start an S, of course, and I don't want AB, right? That would already essentially kill the process. So I'm gonna instead go to A. And oh, well, it looks like I have a BA. So, and it looks like it might be possible if I replace A with BAB, and then if I replace B with BABB, well, I get the string, and so C is actually going to be the only string that can be generated by G. All right, so those were the exercises on kind of reviewing the generation of strings. I hope that's clear. The last part of this tutorial is going to be about context-free grammars. It's going to be a very light and gentle introduction because some of you may not have seen this yet in the lecture, and I don't want to sort of distract you too much from the core material of the midterm. All right, so what is a context-free grammar? Well, as you might already know, it is a grammar G. So it's the standard definition of a grammar G with a set of variables V, set of terminals T, a unique start variable S, and a set of production rules P. Okay, and the only difference from a regular grammar is that a context-free grammar, I can have a single variable on the left-hand side, but I can have anything. So any permutation of strings, terminals and variables, any number of variables and any number of terminals on the right-hand side. So for example, I can say S gives me AAA and ABS. So this is also regular. A regular grammar, as you probably already guessed, okay, that's a 2, is a context-free grammar, clearly. But the other way around is not true. So here, for example, S is context free because, for instance, my variable A is in between two terminals, and that's not allowed in a regular grammar. So this is context free. This is a context free grammar, but not a regular grammar. Okay. And finally, this guy, well, here I'm still restricting myself on the left-hand side to only have a single variable. So this is not a context-free grammar. In fact, this is a context-sensitive grammar, which you're going to see at the end of the course, which is even more powerful than a context-free grammar. All right. So let's look at a few examples. Well, one example and one exercise to close this tutorial on this final topic. So I have the context-free grammar G here, where G is this set of production rules. I have S gives me ASA, S gives me BSB, and S gives me lambda. So what are the strings? What is actually the language generated by G? Well, a trick, the basic trick for grammars also works for context-free grammars, which is you want to list the strings generated by G from shortest to longest, and then hopefully you can see some underlying pattern that's going to come up, and that's going to help you identify the language. So in this case, of course, shortest string is lambda. If I replace S with lambda, then I can also, the second shortest strings are going to be, if I replace S with ASA, I'm going to get AA, and S with BSB, I'm going to get BB. And then in general, if I have S, let's say I replace that with ASA, ASA, and then I replace that with I replace the S here with BSB, and then I replace the S here with, let's say, ASA, so I have AB and BA. So what you're going to notice here is that there's going to be a mirror effect where the leftmost symbol is going to be the same as the rightmost symbol, and the second leftmost symbol is going to be the same as the second rightmost symbol. And so at the end, what I'm going to get is I'm going to get a string of the form W, W, and that's because, actually that's not correct. It's going to be WWR, and the reason for that is because here the leftmost string is going to correspond to the rightmost string here, and in fact the property of this string is going to be, if you reverse it, you're going to, sorry, not the set of real numbers. If you reverse it with the operation R, you should get back the same string, and that's going to be true here because of I know that AB reverse, let me use strings, VW reverse is actually W reverse, V reverse, so W reverse is going to be W reverse reverse, and then W reverse. The reverse of the reverse is itself. I'm going to get W reverse. Okay, so all of the strings that are generated by this context-free grammar are going to have this property, and this has a special name. These guys are called palindromes. So if you want, in general, an example of a palindrome could be something like 22 or 2002. So if these A's and B's were anything else, then that's what the palindrome would mean. It means if you read the string from left to right, it's the same from right to left. And you can see that that's the case for this example here. And more importantly, these palindromes are all going to be of even length. So these are the palindromes of even length. And that's because if you take the length of WWR, well, that's the length of W plus WR, and the length of W is the same as the length of WR. So that just gives me 2 times the length of W, which is even. And so I leave it to you as an exercise, and I'm sure you're going to actually see this in the lecture, so it might not be an exercise, to do it for only palindromes of odd length, and then to do it for palindromes of even and odd length. So I'll leave that to you. Maybe you can try that as an exercise. So the last exercise here is going to be the same kind as before, where we want to know what strings can be generated by the grammar G. So in this case, my grammar G is context free. So I can't use that same trick there where I say, oh, my terminal is ABA, so it has to end with ABA or has to start with ABA. It's not going to be as easy here, right? So for this guy, we're actually going to have to sort of brute force each example and see if there's any derivation that's possible. So for the first one here, AABB, if I start at S, well, there are two things that give me AAs. There's AAB, and AAB. So let's try the first one. I get AAB. And then what can I do? What can I replace each of these with? Well, in fact, it's not going to be very obvious for you, but if you take this direction here, you're actually never going to be able to produce a terminal string. And that's because here the A, the only thing I can replace it with is AB. So I can only replace that with AB. So I'm going to do AB, AAB. And then again, I'm going to replace that with ABB, AAB. And essentially so on, right? So even if I replace all of these B's with terminals, I'm always going to be stuck with that single variable A. And so any derivation is going to, any derivation that takes this path is going to have A and then some terminal strings. So this essentially can never reach a terminal string. We're going to talk about this a lot more when we look at normal forms and when we look at simplifying grammars. But essentially what you should take away from this is that you cannot derive a string W from S gives you A, B, okay? Because you're always going to be stuck with that variable A, okay? And so in general, that means we never actually have to look at this derivation ever again because we know it's never going to be useful. So the only other derivation that we can start from with S is going to be S gives you AAB. And then, well, B can either be replaced with ABA. That's not going to be useful. However, I see where it's going to be useful. It's going to be useful for this exercise, for this choice here. So I can immediately say, so multitasking here, I can immediately say that AABA is going to be generated by G. If we come back to this guy, well, this is not going to help. This derivation is not going to help. What if I use the other one here? If I replace this with S, so if I replace this with S, I get AAS. Again, I don't want to use this guy because I'm just going to be stuck with that variable A. So I need to replace it with AAS. And well, I see I've kind of passed my number of A's here. So that's not going to work. I'm going to be stuck with not being able to generate AABB. And in fact, the same thing is going to happen for AABA, right? I can't use this derivation, so I have to start with AAB. And because the final terminal, the only terminal is ABA, well, that's not going to match because I'm going to have an extra A. So this is not going to work. And lastly, this one, you can kind of almost immediately say that it's not going to be accepted because I know that I can't use this. And so I know that I have to use AAB. and this string starts with BA, so it's impossible for me to start a string with BA, to generate a string that starts with BA. So this is also not going to be possible to generate. Okay, so I realized that I did go a lot over the time. I really wanted to spend a lot of time on those pumping lemma examples because I wanted to make sure that it was clear, and I wanted to make sure that it was thorough. But hopefully that was clear. Again, shoot me an email if it's not, or shoot any of the other TAs if it's not. And until next time, guys. All right, take care.